Today's talk will include the introduction. I will give an introduction of TMD first, and the main materials in this work is MoS2 and WS2, and the application part is hydrogen gas sensors. I will give the motivation of present work, and also the experimental work includes the sensor device fabrication, electrospacing, sample preparation, and measurements. And I will give brief results and discussions of this work, and finally, conclusions. TMD are the alternative materials for graphene, and they are held together by van der Waals forces. And this family with the generalized formula of MX2. And M is the transition metal, typically from group 4-7. And X is a tricogen, such as sulfide, selenium, or tellurium. And also these materials are synthesized mainly by CVD method for making larger and uniform films, and for different applications. 2D TMD materials include noble metals and the metal tricogenides, metal oxide frameworks, organic molecules, and polymers. And the main applications include batteries, electro and photocatalysis, electronics, sensors, and biomedicine. In this work, I will talk about MoS2 mainly, because MoS2 can exhibit good electrical and transport properties, and they are chemical and thermally stable, and they are relatively inexpensive. The carrier mobility is pretty high, and the temperature stability can be up to 1100 degrees. And for application part, this work is focused on hydrogen sensors, because hydrogen is expected to be the common fuel of the future. And also hydrogen is invisible, odorless, and flammable gas. So it is necessary to detect hydrogen leakage in the environment. And also hydrogen has large flame propagation velocity and is highly explosive when exceeding 4 to 75 value% in an enclosed atmosphere. And also for sensors, they should be compact, reliable, inexpensive, and low power consumption, and also with high sensitivity, high resistance, change and fast response, and recovery time. Here shows the literature review of the hydrogen gas sensors. The first hydrogen gas sensor is introduced in 1950. The authors use zinc oxide and gallium oxide. And later, different oxide-based semiconductors materials are introduced for hydrogen sensor applications. And in these oxide-based semiconductors, zinc oxide and tin oxide are proved to be effective. And also, the authors use the platinum as the catalysis. In 2012, MoS2 thin film transistor arrays are fabricated on the flexible substrates, and the authors introduced the use of the platinum and the MoS2 in gas sensors. In 2013, the authors determined the multi-layer MoS2 is more preferable than monolayer MoS2. And also in 2015, the authors introduced noble metal doping for MoS2 and WS2, and these devices are detected at room temperature. However, from the literature review, these references has at least one drawback. For example, in reference 6, the recovery time is too poor, and in reference 7, the working temperature is too high, and in reference 5, the sensor gas sensor doping concentration detection is too low. So In this motivation, we try to make a sensor device with minimized drawbacks. And also, because as I mentioned before, usually the TMD films are fabricated or synthesized by using the CVD method. And in this work, we try to use the aqueous solution method, which is highly challenging. The sensor device fabrication is fabricated by using this flowchart. We use the sulfide substrate. After cleaning, 4.5 micrometer zinc gallium nitride is deposited by using the CVD method. And then we use the mask liner to do the electrode pattern. Then 100 nanometer silver was deposited by using the thermal evaporator. Then we use spin coater to make the MoS2-Pt films. Then the films was annealed at 400 degrees, and finally we get the devices. Here are two electrode patterns shown here, and also the electrode pattern with spacing are 15 and 100 and 150 micrometer. This figure shows the synthesis of MoS2 nanostructure and the deposition of MoS2 films. MoO3 and cereal. Cereal is used as the sulfur source here, and the ratio is 1:20. And the two furnace, the temperature is about 800 degrees for 1 hour, and in argon atmosphere. And then the MoS2 nanostructures was combined with the PMMA and the sulfide system, including these three, and then spin coated at 3000 RPM for 40 seconds. And the sulfidization of the fuels at two different temperatures, which is 400 and 600 degrees. This figure shows the X-ray pattern of the synthesized MoS2 nanostructures, and with two different stabilization temperatures. The black one is 600 degrees, and the red one is 400 degrees. And we cannot see any big difference of these X-ray patterns. However, from the EDS data, we can see the MO to sulfide ratio is 1 to 1.75, which means there are sulfur vacancy. And this sulfur vacancy is very useful for gas sensing. And also, we can see from the EDS data, we can see the PT electrode signal was confirmed in this EDS data. These three figures, the first one shows the electrical response of MoS2 nanostructure for 150 ppm of hydrogen gas at room temperature. This one, and also at 70 degrees. We can see at room temperature, the response time is about 3 seconds, and the recovery time is 2.5 seconds. And at 70 degrees, the response time is 5 seconds, and the recovery is 9 seconds. The second picture shows the sensor response for various concentrations of hydrogen at 70 degrees. We can see there are some baseline resistance drift, which is caused because of the humidity and the effect of temperature and the low concentration of gases. Figure C shows the response of the device at various temperatures to 150 ppm of hydrogen. And we can see as the temperature changes, a considerable change in sensitivity. This flowchart shows the synthesis of MoS2-Pt composite, which is similar to the MoS2 materials. The only difference is we use the H2-Pt Cl6 compound as the Pt resources. And also the nanoparticles was annealed at 390 degrees, and then we can get the MoS2-Pt composite. Also, the X-ray pattern of the synthesized MoS2 nanostructure is similar to the MoS2. And these three figures shows the SPS spectrum of MO3D, S2P, and the PT4F of the MoS2-Pt composite. From these figures, we can see there are no peak shift in the binding energy in the MO and S regions. Therefore, the addition of Pt did not cause any effects in the chemical states of MoS2. These two figures shows the TN image of MoS2 nanostructures and also the MoS2-Pt composite. And also these two figures shows the EDS image of MoS2 and the MoS2-Pt nanoparticle composite. We can see the Pt is about 4.1% in these nanocomposites. This figure shows the schematic diagram of MoS2-Pt nanoparticle composite on a gallium nitride sulfide substrate with SEM images of the substrate before and after the active layer deposition. Why we choose gallium nitride as a substrate? Because it can provide high electron mobility and the power requirements. Gallium nitride devices can perform better along with saving energy, and they have the advantage in comparison with other materials such as silicon carbon, and aluminum. Also, gallium nitride substrate could be used in different applications, such as optoelectronic devices for lasers, solid-state lighting, high voltage power electronics, high performance backlights for displays, UV LEDs, and UV detectors, high power switching devices, and pyroelectric sensors. Why we choose platinum? Because the noble metal functionalization method has been reported to promote the gas sensing performance, and both Pt and Pt metals are well known as excellent materials for promoting hydrogen dissociation, chemisorption, and also platinum addition can promote the gas sensing ability, and the Pt can accelerate the dissociation of hydrogen molecules. Pt can increase the sensor response by increasing the rate of chemical process. Figure A shows the electric response for the MoS2-Pt nanoparticle composite for 100 ppm of H2, and the sensor response can be up to 10. And the figure B shows the real-time response for multiple cycles under exposure to 50 ppm hydrogen gas sense and dry air, and the sensor response can be up to 6. From these two figures, we can see the charge flow increases rapidly when exposed to hydrogen, and it decreases when exposed to dry air. Figure C shows the sensor response of the MoS2-Pt device with various concentrations with 10 ppm up to 500 ppm of hydrogen gas at 150 degrees. We can see from this figure, when the H2 concentration was decreased, there was a change in the resistance with high sensitivity for high concentration of hydrogen. Figure D shows the response and the recovery rates for various concentrations of hydrogen. We can see the fast recovery was due to the platinum catalyst, which caused a high rate of gas desorption at a high temperature. And also, in this figure, the sensor response for hydrogen was pretty high, and the black one is for the MoS2. The red one is for MoS2-Pt devices, and there are 4 different gases H2, H3, NO2, and CO. And the figure F shows the pretty high stability of the device for more than 70 days. Then I would like to talk about the mechanism of these devices. For an N-type semiconductor, it is one where the majority charge carriers are electrons, and upon interaction with a reducing gas, an increase in conductivity occurs. And conversely, an oxidizing gas serves to deplete the sensing layer of charge carrying electrons, and it will cause a decrease in conductivity. So in our device, in step 1, it shows the behavior of PT as an active catalyst, as well as the oxygen absorption. And also in step 2, shows the desorption of oxygen when hydrogen gas is released. The hydrogen molecules will react with absorbed oxygen and release electrons. And the detailed mechanism is shown here. Oxygen molecule absorbed on PT nanoparticle surface during the dry air, and the charge coupling takes place. PT will enhance the absorption of oxygen molecules, and it will cause the reducing of the conductivity by these three equations. And also in step 2, dissociated hydrogen atoms migrate to MoS2 surface from PT to react with absorbed oxygen ions. And also oxygen ions are reduced by releasing the electrons as shown in these three equations. And this will result in an increase in the conductivity. Here is the comparison of our work with other published data. We can see the sensor concentration detection is about 100 ppm, and the working temperature is 150, and the sensor response can be up to 10, and the response time is 8 seconds, and the recovery time is 90 seconds. And compared with other published data, I think these data are good enough. Here is the conclusions. MoS2-Pt devices are highly sensitive towards low concentration of hydrogen gas, and the selectivity of the device showed high response to hydrogen and poor response towards other gases, and the selectivity can be up to 70 days. And also, our device shows very low detective limit upon exposure to hydrogen compared to previously reported 2D nanomaterial-based hydrogen sensors with PD MoS2 composite or PD functionalized MoS2. And here is the final results here. And by the way, because of the time is limited, I will briefly show our another devices, zinc oxide and MoS2 nanostructures here. And we use the glass substrate, zinc oxide 200 nanometer, and then MoS2 nanostructure. Here is the material calculations here, and here is the performance of our devices. And in this figure, the response time is about 7 seconds, and the recovery is 23 seconds. And the ultrafast response time was attained because of the MoS2 catalyst increasing the rate of diffusion and dissociation of the hydrogen molecules. And the stability can be up to 50 days. And also, it also shows good selectivity towards hydrogen gas. Here is the conclusion of these devices here. And here is the reference. And National Cheng Kung University is at the south part of Taiwan. And the weather is pretty warm. And there are different students from various countries working in our lab. So we welcome all the master and the PhD students to join our lab and the university. Okay, here is the photos of our group members.